Hello everyone. So now we're gonna shift gears from the op amps, the MOS amplifiers, and we're gonna completely kind of reset the class and start on a whole new topic. So basically we've concluded all our amplification part of the class. And now we're going to actually get back into circuit solving. But unlike in the 2K1 class where you focused on solving circuits either for the steady state when you did spacers, or when you assumed DC sources and looked at resistor networks, now we're actually going to look at the full dynamics of circuits with arbitrary time varying signals. And it's going to take a while to kind of develop the full machinery to actually do this analysis. But before we could even do that, we have to introduce a number of mathematical concepts that we will be using to solve circuits. So in particular, what I've done is I've split these lectures into three parts. And the reason I've done this is because, for example, this lecture, it's an introduction to ordinary differential equations. And many of you might have already taken a class on differential equations, so you know everything about them and you know how to solve them. But some of you, since differential equations is only a core requisite, might actually just be taking the class, and so I need to make sure that we're all on the same page. So this particular lecture will actually go over some very basic ways that we will be solving differential equations in this class so that you can actually solve the circuit question or analyze the circuits that will be giving you. So basically, we're going to have three lectures. And this first lecture will focus on differential equations. So basically this one will focus on how to solve ODEs or linear ODEs. And we're going to define what a differential equation is on the next slides if you still don't know what that is. I'm guessing at this point of the semester you do know what it is, but if you don't, we're defining everything. Now, if it turns out that you already know how to solve differential equations, if I give you a differential equation, you might as well skip this video or skim through it. There's no need to watch it because that's all I'm going to do in this video. Now, the next video we will actually be going over how to derive differential equations from circuits. So how to go from kind of a little circuit, you might have a capacitor, an inductor, into, and then you have kind of something inputted to this. Doesn't matter what it is. And then how do you get your differential equation from the circuit? So that's going to be the next video. And then finally, the third video, which is actually, believe it or not, the one that we care about the most in this class, which is the third, we will be analyzing and characterizing first and second order circuits. So in this class, we're actually teaching you all this ODE stuff, mostly because we want you to understand the kinds of things you can get out of circuits. And that's where the characterizing parts comes out. So in particular, what we're going to look at is, first of all, how to analyze these circuits. But then we're going to look at how you can modify these components and how that changes your responses to the responses of these circuits to different inputs. And so that's going to be kind of the three lectures that kickstart this this section of the class. Do realize that we are giving you some very simplistic, in this lecture I'm going to give you some very simple methods to solve differential equations. There are much better ones. And actually later in class, in about 7 lectures or 8 lectures, we're going to introduce Laplace transforms. And that's actually the method that we want. Oh, actually, we're going to introduce convolution and then Laplace transforms. And those are much more superior methods than I'm going to show you today. But these initial methods, it's mostly to get you going, to get you understanding some of the theory, and yeah, so we're gonna develop a lot more on this. So like I said, if you're a professional on how to solve differential equations, you can probably skim through this video. I'm actually going to go over a long range of examples, and for those of you that are more, you might actually get a little bored. What I've noticed in the past is that if students are taking ODE simultaneously with this class, they have a lot of trouble with this section. So that's why I decided to go over extra examples. And then students that don't need them, they can just skip them. That's why you can always fast forward. So it's not a big issue. What is a big issue is if you don't have enough examples and you don't understand the material. Now, the second lecture actually focuses on deriving the ODEs. So if you're that kind of person that, let's say you know how to solve the ODE, but you don't actually know how to get the ODE from the circuit, you want to pay extra attention on that video. Now, if you already know how to derive the ODEs, but don't know how to solve the ODEs, then you don't want to pay attention to that video as much as you want to pay attention to this video. So do realize, kind of depending on where you get stuck on a problem, you might want to rewatch or watch more closely each of the videos. The third video, which I would say is the most important one for this class, is where we actually put it all together and kind of give you an idea as to what the solutions to these problems tell you about the circuit. And so that one is very important that you watch and that you understand everything in, because that's actually the whole reason we're teaching you 1 and 2 is so you can understand 3, basically. And so it's important that you actually understand everything in 3, because that's going to show up in an exam. And it's also like what we actually care about as electrical engineers. Differential equations at the end of them, and they are mathematical concepts. But circuits are not, and we're just using these mathematical concepts. So you need to understand the implications from a circuit standpoint, which is 3. But to understand those implications, you need to know the math and so on and so on. Anyway, I'll stop wasting time. It's already been 7 minutes. So let me get started. So the first thing you might be kind of wondering about is, what is a differential equation? And in particular, in this class, we're going to focus on linear differential equations with homogeneous coefficients, meaning that the coefficients in front of each derivative term are constants, and there's no quadratics on the unknown function. Okay, in general, a differential equation is just simply an equation such that you have your unknown quantity. So this could be a voltage across a capacitor, with itself as long and a bunch of its derivatives. So in particular, we call an nth order differential equation if the nth order derivative, or the highest order derivative that's available, is of order n. So later on, we're going to look at a bunch of circuits, and we're going to get a bunch of things kind of like d dt of I squared of t plus d dt of I, and then there's going to be a coefficient 1, which could be, let's say, 7, and then 5 plus I of t, there should be a t here, equals some function here. So this could be kind of the voltage in of t. So we're going to derive a bunch of these for the circuits. This is what we would call a second order differential equation, because we have a second order on that's the highest order derivative that you can see. And additionally, it's inhomogeneous because the right-hand side doesn't have a 0. So if the forcing term or the input voltage for the differential equation were set to 0, that's what we call homogeneous. If it's not 0, we call it inhomogeneous. Yeah, so basically this kind of summarizes what a differential equation is. It's just an equation of this form, where you just have a bunch of numbers, a0, a1, a2, multiplying a bunch of derivatives of the function. And for our purposes, those could be currents across an inductor, voltages across a capacitor, voltages across a resistor, currents across a resistor, and whatever. There's some circuit-related quantity that when we derive equations, we're gonna get. And the differential equation or ordinary differential equation is called ODE. It's called homogeneous if zero is kind of the input or what we call the forcing term. And it's homogeneous if the forcing term is non-zero. Okay, so that's basically what a differential equation is. First, we're going to look at a variety of examples. In particular, in this class, other than in the homework, you might be asked to solve a third order one. We're only going to be looking at first order and second order differential equations. So now we're going to actually look at some examples, more concrete examples of these. Okay, so first I'm just going to go over how to solve a homogeneous ODE, and I'm going to focus on the first and second order cases. First, I'm going to give you a general recipe, but then I'm going to go over a variety of samples for those. Okay, so let's go. Okay, so how do we solve homogeneous ODEs? So let's just for a little bit plug into this equation a guess for x of t of e to the lambda t. And let's just see what happens. So I'm going to have a0 e to the lambda t plus a1. And remember, the first derivative of e to the lambda t is just lambda e to the lambda t. So just remember that the dt to the ith order of e to the lambda t is just lambda to the I e to the lambda t. So for the second order, I'm going to get a2 lambda squared e to the lambda t plus dot 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 plus an e to the lambda t lambda to the n. And since so that's on the left hand side I have 0, and then I'm going to get that on the right hand side. I can factor out all the lambdas and the a's, or I can factor out e to the lambda from each term. So this is actually equivalent to saying a0 plus a1 lambda plus a2 lambda squared plus a3 lambda cubed plus dot 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 plus an lambda to the nth power e to the lambda t. And that all has to be equal to 0. So one thing to note is that this has to be valid for all time. And we know that, for example, at time equals 0, e to the lambda t will be actually equal to 1. And so this cannot be 0 for all time. And so this thing must be 0. And so as a result, the equation that we actually have to solve to determine the solution is we have to find the roots of this polynomial. And we actually call this polynomial something special, which is the characteristic polynomial. Characteristic polynomial. Now, as you can see here, the difference between this equation and this equation is that I've replaced a 0th order derivative, or the function itself, by lambda to the 0th power, a first order derivative by lambda to the first power, this is to the 0th power, a second order derivative by lambda to the second power, and so on until I got to an nth order derivative with lambda to the nth power. So in general, the characteristic equation just simply replaces each order of derivative with a power of lambda. So x of t gets replaced with 1, or lambda to the 0. dx dt gets replaced with lambda, or lambda to the 1. dx dt squared gets replaced with lambda squared. dx dt cubed gets replaced with lambda cubed, and so on and so on. So to go from a differential equation to its characteristic polynomial, you just replace derivatives with powers of lambda. Okay, so what's so important about this? Well, if we find the roots of this polynomial, or we solve this characteristic equation, that will give us the values of lambda that will lead to solutions to this differential equation. Okay, so let's say we factor this polynomial, so now we're going to get kind of lambda plus, we're going to get an, lambda plus lambda 1, lambda plus lambda 2, lambda plus lambda 3, and so on up to lambda plus lambda n. As it turns out, our equation will actually follow, sorry, and this should be not plus. Should be a minus here. Minus, 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 minus. So the roots are lambda 1, lambda 2, lambda 3, lambda 4 up to lambda n. Because if I plug in for lambda 1, I'm going to get 0. If I plug in lambda 2, I'm going to get 0, and so on. So at this point, any x of t of the form constant 1 e to the lambda 1t plus constant 2 e to the lambda 2t plus dot 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 cn e to the lambda nt will actually result in satisfy our homogeneous equation. So basically, this is the solution to our ordinary differential equation, and we can pick our coefficients c1 through cn arbitrarily. They could be any number that we want them to be. As it turns out, in order to be able to actually come up with the dynamics of the system, we're going to need as many initial conditions, or we need to know the values of our voltages at certain time periods in order to be able to figure out what the appropriate coefficients should be. And we're going to go over some questions in the next few slides. Now, there could be the case where you have a repeated root. So for example, you could have that lambda 3 gets repeated. So now you have plus, so this becomes kind of lambda 3 squared. And then this would go to n minus 1, or sorry, not cube, 2. When you have repeated roots, you will have two solutions associated with that repeated root, and they will be of the form e, so c3 e to the lambda 3t plus c4 e to the t times e to the lambda 3t. And let's say I had a third repeated root, then I would add a fifth term, t squared e to the lambda 3t. In this class, we'll only see these two cases. We're not going to go further than that. But in general, if you have degenerate roots, you just keep adding powers of t up to the order minus 1 of the number of times that you have that repeated root. And those still will be homogeneous solutions. All right, so that's basically the solutions to homogeneous ODEs. And the way we came up with them is we basically made a guess that our solution was e to the lambda t. We plugged it into the differential equation. And then we got that lambda had to satisfy this equation, what we call the characteristic equation. And then we came up with the roots, and that gave us our solution. Okay, so just to summarize, again, here I actually have written what I wrote in the other slide much more cleanly. So we started with a guess. We plugged into our equation e to the lambda t as a guess for the solution for x of t. And then what we ended up getting was that the lambdas that would actually allow us to satisfy the equation, the homogeneous equation, were the roots of this polynomial, which we called the characteristic polynomial. And that characteristic polynomial just basically replaced all the powers of derivative with powers of lambda. And additionally, we said that we could find the roots of this polynomial. And if all the roots were different, our final solution would have a form of a linear combination, or a combination of all the different roots with arbitrary coefficients that we could be find if we knew some initial conditions. We're going to go over examples later as to what I mean by initial conditions. Additionally, we said if we had repeated roots, so if we had the ith root appear more than once, so if it appears m times, we would basically have coefficients, and then each time, so this would be the first coefficient would have t to the 0, the second coefficient would have t to the 1, up to the t to the m minus 1 times e to the lambda I t. So those are the two caveats that we had in our equations, and now I'm actually going to go over some examples of this to make this more concrete. So this is actually all of the theory. If you understood this, you probably don't need the examples, but now I'm going to actually go over some more concrete examples. Okay, let's say we want to solve for this differential equation, and in this particular case, they gave us the value of our solution should be at 0. So just so you remember, we have to find the characteristic equation. So in this case, it would just be a0 plus a1 lambda. I'm going to actually just make my guess of e to the lambda t and plug that into the differential equation. So I'm going to get basically a0. So if my solution is of the form e to the lambda t, I have to have that a0 e to the lambda t plus a1, the derivative of e to the lambda t lambda, e to the lambda t, have to be equal to 0. And so that really means that a0 plus a1 lambda, e to the lambda t have to be 0 for all time. So the symbol here means for all time. Now, at time equals 0, this is 1, so that means that this thing has to be equal to 0, or my characteristic equation has to be equal to 0. And so that gives me that lambda is actually equal to negative a0 over a1. Okay, so that means that now my homogeneous solution, or xh, so we're going to denote the homogeneous solution to an equation as hh, is going to be equal to c1 e to the negative a0 over a1 t. Now, we don't know what this constant is, but they gave us the value of our solution at time equals 0. So we're just going to say here x of 0 equals c1 e to the negative a0 over a1 times 0. Which has to be equal to 5. Well, at time equals 0, this is just equal to 1, because e to the 0 is just 1, so we have that c1 is 5, so we have that x of t is going to be equal to x of 0 e to the negative a0 over a1 t, which is just really equal to 5 e to the negative a0 over a1 t. So this tells us that c1 is equal to 5. Okay, so that's actually how you're going to solve differential equations. In the next slide, I do it a little bit more cleanly. So like I said, we can plug in e to the lambda t into our equation, and that's just going to lead us to our characteristic equation, which is just a0 plus a1 lambda equals 0. And then we need to come up, that allows us to solve for the roots of this equation, which are the values of lambda. And in this case, we got that this was the root, and then we used our initial conditions to find the solution. Okay, now we're going to look at a second example. In this particular example, there is a second order derivative. So this is a second order ODE, and it's homogeneous because the right-hand side is 0. We still don't know how to solve in homogeneous, and I'm actually going to go over that a little later. Okay, so at this point, you can actually find the characteristic equation. So it would be 6 plus 5 lambda plus lambda squared equals 0. I'm going to do it one more time, going over the old method just to kind of show you that this indeed is true. So we're going to basically plug in 0 equals 6 e to the lambda t plus 5 lambda e to the lambda t plus lambda squared e to the lambda t. So we basically plugged in e to the lambda t into our differential equation, and that led to 6 plus 5 lambda plus lambda squared e to the lambda t. And so as a result, this has to be 0, which is our original characteristic equation. So in general, we're just going to, in the next few examples, we're just going to look at the characteristic equation. In this case, we have that our roots are actually, this is actually lambda plus 2 or lambda plus 3. We can use the, what is this, the quadratic formula, so negative b plus minus 2ac, which in this case, right, 2a, so in this case it's just 2. The square root of b squared, which is 25, plus 4ac, so 4 times 6 is 30. Wait, 4 times 6, sorry, 24. Oh, sorry, and it's minus 4a6, so 4 times 6 is minus. So this is actually just equal to 1. And so we're going to get that our roots are 5 minus 1, which gives us 4, divided by 2, which gives us 2. And then 5 plus, sorry, God's here. We're going to have negative 5 plus 1 over 2, which is just negative 2. And then we're going to have negative 5 minus 1 over 2, which is just negative 3. Well, that's basically these two. Okay, so we got our roots, whatever. I mean, you can just do this by inspection, but you could also have used the quadratic formula. And now we need to figure out what the homogeneous solution is. So in this case, it's just going to be x of t homogeneous is just going to be constant 1 e to the negative 2t plus c2 e to the negative 3t. So since lambda 1 is negative 2, then we have a negative 2 on the first one. Since lambda 2 is negative 3, we have negative 3 on the second one. And now they gave us two initial conditions, so we can find these two coefficients. So the first one is that the value at 0 is this, and the derivative at 0 is 5. So we have to take the derivative of this expression. So we're going to have that d dt of x homogeneous of t is actually equal to negative 2c1 e to the negative 2t plus minus 3. So minus 3c2 e to the negative 3t. And okay, now we can plug in our initial condition. So we're going to plug in 0 for t, 0, 0. So we plug in 0 here, we plug in 0 here. So we're going to get, and that should all be equal to 3. So we're going to get c1 plus c2 have to be equal to 3. And then in this one, we're going to get, that has to be equal to 5. And we have negative, we need to plug in 0 here and 0 here. So 0 times 0. And that's going to give us negative 2c1 minus 3c2. And then we can basically calculate what the two coefficients are, which I did in the next slide. So we're going to take it from there on the next slide. Okay, so just to recap, we found the characteristic equation. We determined what the lambdas were. We found our homogeneous solution. We took its derivative, and then we plugged that into our initial conditions in order to get two sets of equations. So we got this equation and this equation. It turns out that you can actually solve those two equations for C1. So basically, you can take this equation and say that C1 equals 3 minus C2. And then plug that back into here to get C1. And then once you get C1, then you can plug it into the first equation to get C2. And so once we found the two coefficients, we basically can now get the value of our solution. You can plug this back into your equation to show that indeed it satisfies it, and the initial conditions are also satisfied. So x of 0 would be 14 minus 11, which gives us 3. And the derivative at 0 is also going to give us 5. And when we plug this into our equation, since we used our their solutions to the characteristic equation, it will give us 0. Now, for second order, remember that whenever you have second order roots, you can either have 4 cases. You can have roots that are either real, distinct. You can have real, same, so you can have repeated roots. And then you can have complex roots. And then you could also have imaginary roots. In this particular case, we had that both roots were real and distinct, so we had this first case. And we're going to call that in this class overdamped. We're actually going to go over more of this in the third video where we try to characterize circuits by its type of response. So whenever circuits generate 2 distinct roots, we're going to call that overdamped. So this is more for next lecture. Now I'm actually going to go over examples for each of these cases for the second order, and then we're going to look at inhomogeneous ODEs. Okay, so let's look at our second example. Okay, so for this second example, again, in order to solve this, I recommend you could also pause this video and try this on your own at this point, and then I'll go over it. That might actually give you some extra practice, but I'm going to go over it now. So remember, the first step is just figure out the characteristic equation, and I'm going to stop plugging in e to the lambda just because we know already what's going to happen. This will become a 4, this will become 4 lambda, and then this will become lambda squared. And now we need to find the roots of this particular equation. And for this particular case, what we're going to get is actually that this is equal to lambda plus 2 squared. You could also use your quadratic formula, so you have negative 4 divided by 2a plus minus the square root of 4 squared, which is 16, minus 4 times 4, which is 16. And so you get a repeated root of negative 2. So you see how the quadratic formula gave you a single root, so that means that you have a repeated root of 2. Okay, so for this particular case, since we have a repeated root, our homogeneous solution will actually look like this. X of t equals e to the lambda, or sorry, not lambda t, sorry. So constant 1 e to the 2t plus constant 2 t e to the 2t. And additionally, when we take the derivative of this, we're going to get, wait, this should be negative 2 because the root is actually negative 2, not 2. We're going to have x of t, the derivative, is actually equal to negative 2c1 e to the negative 2t plus c2 e to the negative 2t minus 2 c2 t e to the negative 2t. So I used the product rule on the second term. That's why I got these two terms. So basically, you take the derivative of this term. You're going to first take the derivative of t, which gives you c2 e to the negative 2t. And then you take the derivative of e to the negative 2t, which gives you negative 2c2 t e to the negative 2t. Okay, at this point now, to figure out what C1 and C2 is, I have to plug in my initial conditions. So I'm going to plug in 0 into this equation. So I'm going to have 0, 0, so times 0. And then I'm going to have a 0 here. And then I'm going to have a 0 here. So this equation will actually be turned into C1 equals 1. So now we know what C1 is. And then I'm going to plug in 0 here. I'm going to plug in 0 here, I'm going to plug in 0 here, and then I'm going to plug in 0 here, and then I'm going to plug in 0 here. So this will become equal to negative 2c1 plus c2, And then this 0 here cancels out this term, so we're going to get that that should all be equal to 0. Sorry, that should all be equal to the other initial condition, which is 2. And we know that C1 is equal to 1, so we have negative 2 times 1 plus C2 equals 2, and that's going to give us that C2 equals 4. Okay, so that's basically it. In the next slide, I actually kind of go through the full process, so I'm going to show. Okay, so we found our roots in our previous slide to be negative 2 and negative. So we had repeated roots, and then we said that this would be the form of the homogeneous solution. Because we have repeated roots, now we end up with the second term with the t and the term. And then we took the derivative of that term. We used product rule to take it into two terms. And now we basically have here the value of x of 0. And in particular, we're going to get that C1 equals 1. And then we have that C2 equals 4. So our final solution will look like this, where C1 has been replaced with 1 and C2 has been replaced with 4. In particular, we're going to call these kind of repeated root solutions when we look at circuit as critically damped, and we're going to go more over that later. Okay, so now let's look at another example. So this particular example, we're going to have that our characteristic equation is actually 0 equals 4 plus lambda squared. And that's going to give us basically plus minus the square root of 4, negative 4 AC, which in this case is 4, divided by 4. So, sorry, divided by 2. And so here we have 16, right? Minus 4 AC divided by 2A. And so this will give us actually that this is plus minus I4 over 2, which is just this plus minus I2. Sorry, I'm going to use a J since we're in electrical engineering world. So J means imaginary. Okay, so for these particular roots, our homogeneous solution would be of the form C1 e to the negative I 2t plus C2 e to the I 2t. We're actually going to not use this notation in this class. We're going to use sines and cosines. So we could use Euler's identity to rewrite this as C1 times cosine 2t plus, or sorry, minus I sine 2t. And then we can write our C2 times cosine 2t plus I sine 2t. And then we just can combine all the like terms. So we're going to get basically C1 plus C2 cosine 2t plus I C2 minus C1 sine 2t. And we're just going to call this number B1. And I'm going to call this whole thing B2, so that I'm just going to say that the homogeneous solution is just B1 cosine 2t plus B2 sine 2t. So whenever you have imaginary roots, you're just going to automatically, instead of using your imaginary exponentials, you're just going to assume your solution will be of this form. So in the future examples, I'm not even going to bother going to the complex notation. Okay, so again, we have our initial conditions. So we need to figure out the derivative of this. So in this case, we're going to have that d dt of x of t is actually going to be equal to, well, the derivative of cosine is negative sine. So we're going to have negative 2b1 sine 2t plus 2b2 cosine 2t. And now we can just apply initial conditions. So we have that x of 0 is equal to 2. So we're going to, from this, we're going to get that b1 times 1 plus b2 times 0 has to be equal to 2. And then from this second equation for the derivative, we're going to get that negative 2b1 times 0, which is the value of sine at 0, plus 2b2 times 1 has to be equal to 6. And then we can solve this equation. So b1 is going to be 2, or the value at x of 0. And once we know b1, then we're going to get that, we can plug that into here to figure out what, actually, b2 is just going to be the second initial condition divided by 2, which is just 3. So in the next slide, I'm going to do this more cleanly. Okay, just to reiterate, we're not going to use this notation when we have complex roots. We're actually going to split it out into sines and cosines. And we're going to define these coefficients b1 and b2, which is just the sum of the two coefficients, and then imaginary the difference. And we're actually just going to solve for b1 and b2 instead of c1 and c2. Okay, when we take the derivative of this expression, we're going to get negative 2 sine and positive 2 cosine. And then when we plug in 0 to the equation, we said that we would just get b1 equals 2. And here we get 2b2 equals 6, so that gives us b1 equals 2 and b2 equals 3. And then finally, we just get our final solution by plugging in the coefficients. We're going to call this solution undamped later when we solve circuits. Undamped meaning that there's no damping because it's just a sine and cosine, but we're going to talk about that in the third lecture of this series. Okay, so we have one last example, and I'm just going to go over it very quickly. And this is the case when we have complex roots. So they're neither purely real, neither purely imaginary, nor the repeated roots. So for this particular case, if you look at this polynomial, we're going to have basically 5 plus 2 lambda plus lambda squared is our characteristic equation that equals 0. That leads to a quadratic formula of negative 2 over 2 plus minus the square root of 4 minus, so we have b squared minus 4 times a times c, which in this case is 5. And so we end up with basically, well, this is 20. And then 4 minus 20 is 16. So we get basically negative 1 plus minus, the square root of 16 is 4. So we have I4 over 2. And so we end up with basically these two. And remember, oh yeah, and we're in electrical engineering world, so there should be a J, not an I. Okay, so our roots are actually negative 1 plus or minus J2. Okay, so just like we did before, we're going to use Euler's formula to write this in the form of the real part of the exponential will have e to the negative lambda, and then the imaginary part will be written in terms of a sine and a cosine term. So if you have a complex root, you're going to have the real part as your decaying exponential and the imaginary part as your cosine and sine. All right, so once we have this, we need to take the derivative in order to be able to apply initial conditions. I have to apply the product rule. So first I take the derivative of this term, so I get negative e to the negative t cosine 2t. Then I take the derivative of this term, so I get negative 2 e to the negative t sine 2t. Then I take the derivative of this term, so I get negative b2 e to the negative t sine 2t. Then the second term, I get 2b2 e to the negative t cosine t. So basically I have to apply the product rule to ice in order to take the derivative of the full solution. Now I apply my initial conditions. So for x of 0, we have b e to the negative 0 cosine of 0, which is just 1, and this is just 0. So that means that this whole thing goes away, and that gives us that v1 is equal to 2. Yeah, so now once we know v1, we can plug that into our differential equation. And so we have that v1 is equal to 2. And then so here we have 1, so that one actually becomes just b1. This one is negative 2b1, but then there's a sign, so that one goes away. This one has a sign, so it goes away. And then we are only left with the 2b2 as my second term. And so we have negative 2 plus 2b2 equals 1. So we move the 2 to the other side. And then that ends up giving us 3/2 for b2. Once we have the 3/2 for b2, we just plug that into our equation. For b1, for b2, 3/2, and so we plug that into our equation, and finally we have our final solution. Okay, so we've gone over several examples on how to solve ordinary differential equations and the procedures that we're going to use in this class. But we've done that only for homogeneous. So the question now is, well, how are we going to deal with inhomogeneous cases? Well, what we're gonna do is we're gonna take our homogeneous solution and we're just gonna add an extra term to take care of that inhomogeneous ODE. So in particular, for now, what we're gonna do is if we're having to solve this differential equation that I show here, where the forcing term is y sub t, we're gonna assume our solution is the same as before. And of course, if we have repeated roots, we have that like one little caveat. Except now we're going to add this extra term with a coefficient C0 that's of the form of y sub t. And remember that to find these, we had to use our initial conditions. Well, we still have to use our initial conditions to find those, but now we have an extra coefficient. And so we're typically not going to have enough initial conditions to figure out what C0 is. So what we're going to actually do is we're going to take our solution and we're going to plug it into our differential equation. And we're going to use that to find what our coefficient is. Now, when we plug this full solution into the differential equation, you have to remember that these terms here all satisfy the homogeneous solution. As a result, when you plug the whole thing into the differential equation, the only term that will give you a non-zero contribution will be the y sub t part. And so what you're going to have to solve is an equation of this form. Y sub t equals the sum of the derivatives of C0 y sub t. And that's basically how we're going to come up with our solution. So this might look like fairly complicated, but it's actually quite simple. I will go over a few examples and you'll see on how to apply this, because I think that's the best way to actually understand what I mean by this. Okay, so let me go to the next slide. Okay, so let's look at our previous example. So in our previous example, first order example, we had that basically the same differential equation, except now the right-hand side was 0. Let's say now our right-hand side is 2e to the negative 3t. Let's try to solve it. So from our previous example, remember that we said that the solution was always e to the negative a0 divided by a1. And in this case, a0 is 4. And a1 equals 2. And so that's going to give us e to the negative 2t. And so now we get that basically our total solution will be of the form of the homogeneous solution, or c1 e to the negative 2t, and a part that's of the form of the forcing term, which in this case is e to the negative 3t times a coefficient c0. So to find C0, we plug into our differential equation. So basically, I'm going to take our solution and I'm going to plug it into our differential equation. And what I'm going to get is, when I take these derivatives, one is just going to be negative 3 C0 e to the negative 3t, and the other one negative 2 C1 e to the negative 2t. So here I actually went through that all that arithmetic. In general, because this satisfies the homogeneous solution, you're going to have that all of the e to the negative t term, 2t terms will cancel out. So you're just going to be left with this one and this one. So we have 4c0 minus 6c0, which becomes negative 2c0 e to the negative 3t. And that should all be equal to 2 e to the negative 3t. So that gives us that c0 has to be equal to negative 1. Okay, we know c1, c0, so we can plug it in. And now we can use our initial condition to figure out c1. So in this case, we're going to have, this is negative 1 at time equals 0. And then we have that this is c1, so negative 1 plus c1 has to be equal to 5. So that gives us that c1 is 6. So our final solution will be this. So you see how easy it was to apply that? All we did is we took our previous solution and we added this other term that's of the form of this term here. And then we plugged that to figure out what this constant was. We plugged it into the differential equation. So I'm going to go over another example. Okay, so in this particular case, we have a new differential equation. And just to reiterate, we've said that if this was a 0 and this is a 1, well, here I can actually just derive what the homogeneous solution is. So we have 6 lambda plus 2 equals 0, sorry, 6 plus 2 lambda equals 0, which gives us that lambda equals negative 3. So we have c1 e to the negative 3t. Okay, so like I said before, we're always going to take the form of the forcing term. In this case, our forcing term is a constant. So we're just going to have c0 plus a homogeneous solution. It doesn't matter what our homogeneous solution is, because when we plug this back into the differential equation, the homogeneous part will disappear. And so we're just going to get basically 3 equals 6 times c0 plus 2 times the time derivative of c0, which is just 0. So this just kind of gives us 6 times c0 is equal to 3, which then tells us that c0 is equal to 1/2. Okay, so now once that we know c0, we can find the homogeneous solution. So here I found it. It's just c1 e to the negative 3t. So we have basically 1/2 for our, what we're going to call the particular solution, And then here's our homogeneous solution. And then here's our initial condition. I subtract 1/2 from both sides, and I'm going to get that c1 is 4, and then I get that this is the solution. Okay, so that's another example. So let's just go over one more example, and we can wrap this up. Okay, so let's look at a second order ODE. So like I said before, in this particular case, our forcing function again is a constant. So that means that we're going to assume that our solution is of the form of a constant c0 plus our homogeneous solution. When we plug that back in, the homogeneous solution part won't affect anything. So we can just not even plug it in. So we're going to get basically 6 is equal to 6c0 plus 5 times ddt of c0 plus ddt squared of c0. Well, the derivative of a constant is 0, and the second order derivative of a constant is 0, so we're just going to get 6c0. And so that's going to give us that c0 equals 1, which is what I wrote here. And now we need to actually find the characteristic equation for this, so we're going to have 6 plus 5 lambda plus lambda squared, and that's actually equal to lambda plus 2 lambda plus 3. So you can go and plug that into your quadratic equation, and then you can get what the roots are, but they're -2 and -3. And so once we find the roots, we know that our solution will be C1 e to the -2t plus C2 e to the -3t. And then finally, we have two initial conditions here, which we can use to find our solution. So in this case, we have 1, which is our particular solution, particular. So remember, that's what we're going to call the part that's due to the inhomogeneous equation. And then this would be the homogeneous solution, homo. And then we evaluate it at 0, so we're going to get that 1 plus C1 plus C2 equals 4. And then we take the derivative of the equation to get, when we take the derivative of 1, we get 0. So we're just going to get, for this one, we're going to get -2C1, and then for this one, -3C2. And then, so we're going to have these two equations, and then we can use those to solve for the coefficients. And then finally, we're going to get that this is our solution. Yeah, so that's basically it. The only thing that changes now is that before we find plug in our initial conditions and find our homogeneous solution, we need to figure out what this C0 is. So that's in general the way we're going to solve these differential equations. Okay, so now that we've gone over all of those examples, I'm going to actually kind of summarize with a heuristic of what we're actually going to do when we solve differential equations. So in particular, what we said we were going to do is we were going to separate our solution into two parts. One that's of the form of the forcing term, or y sub t. And that one we're going to call the particular solution, or x of xp. And then the homogeneous solution, where this is actually the homogeneous. And then what we're going to do is to find the coefficient, or C0. To find C0, we're just going to plug in x particular into our differential equation. The reason we don't plug in homogeneous, x homogeneous, is because it doesn't actually contribute anything to our differential equation. Because remember, when we apply the differential equation to x homogeneous, we're just going to get 0. Okay, so we plug in this into our differential equation, and then we try to solve for C0, which in this case I'm calling CP, but I mean C0. Okay, so that's actually going to turn out to be the value of y sub t divided by whatever this is. So let's assume, for example, that y sub t is equal to e to the -2 lambda t. And just for argument's sake, let's just say we have kind of 2 C0 e to the lambda t, e to the -2t plus 3 ddt e to the -2t. So you would take all the derivatives, and then what you're going to see in the end is that the time variation will cancel out, and you will be able to solve for C0 effectively. Okay. Yeah, so that's kind of that's basically what so once we have C0, which we derive by plugging in our particular solution into the differential equation, then we basically take our total solution and use that to find the coefficients for our homogeneous solution. So first we need to find the characteristic equation. We use that to find the roots. Once we have our roots, we get that the homogeneous solution is of this form. And then we plug in all our initial conditions in order to come up with what these coefficients have to be. And that's basically it. That's what I've been doing in the previous slides. This might look a little bit abstract, So if you don't quite follow it, make sure you can follow the process that I did in the previous 3 examples. Okay, so this actually concludes everything you need to know about solving differential equations for now. In the next slide, in the next class, I'm actually going to talk about how to derive differential equations from circuits. And then the last class, we're actually going to look at a number of circuit examples. Okay, thank you.